Hi everyone. So my name is Yan, and I'm a principal engineer here at the DAZN. And I want to start by talking about what happened in 2014, because a lot of things happened, including Taco Bell announcing that they've got a breakfast menu, which is, wow.
Really?
Who thought, right? And of course, you got something really cool. Like Alibaba had the biggest IPO at the time, at $25 billion, which is pretty mind-boggling. And then we also had the Grumpy Cat, and of course, Frozen came out, so everybody was singing "Let It Go" on the street. So it was interesting times. And amongst all these interesting things happening in 2014, Amazon also announced this thing called Lambda. And since then, we got this whole serverless paradigm thing people keep talking about. And ever since 2014, I've been playing this wonderful game whereby every time I talk to people about serverless, someone points to me that, but there's still a server somewhere, which it is a great game. You can't play quite as well as back in 2014, but occasionally I still get odd people telling to me, so, of course, that's entirely missing the point, because serverless is serverless in the same way that wireless is wireless, even though there are still wires hanging around somewhere, but it's not what you are concerned about. It's not what you care about when you want to connect to a wireless hub. In the same way that serverless has got servers, but it's not your problem anymore. And we did argue quite a lot for a long time in the community in terms of how do we actually define this serverless thing. And I think eventually we've settled down on three things. And serverless is anything that any technology that you don't pay for it when you're not using it, and it's any technology that you don't care about setting up the scaling, the managing the server, the provisioning of servers, and so on. And you also hear people talk about function as a service, which is very similar, I guess a very related term compared to serverless. And that's where you're going to find the poster boy for serverless, including Amazon Lambda, and then Google Cloud Function, and Azure Function as well. And I think function as a service is a lot closer to what you actually get on a day-to-day basis, whereby you write a piece of code, just a simple function, and then you let the cloud provider trigger your function when some event happens. And it could be someone hitting an HTTP endpoint somewhere. It could be a file being dropped into S3, or someone publishing an event into IoT Hub, or into Kinesis, or into SNS. Or you can have a cron job schedule in CloudWatch to trigger your function as well. And when you compare function to service as a paradigm to infrastructure to service, container to service, and platform to service, of course, it's going to be closest to platform to service. The main difference being that your unit of scaling is now down to the function level as to the application level. And just because something is function to service doesn't necessarily mean that it's serverless. If you take something like Kubernetes, for example, which allows you to run function to service on top of your own Kubernetes cluster. But guess what? If no one is running compute load on your Kubernetes cluster, you're still paying for that cluster yourself. It may not be your developer's responsibility to maintain that, but ultimately as an organization, you're still paying for it. So by our definition, Kubernetes and OpenWhisk and many other platforms like that, they are function to service, but not serverless. Equally, you have database solutions or data bus solutions. I'm doing really well there. That like DynamoDB, where you don't need to worry about maintaining something, you don't need to worry about scaling and all of that, which is not entirely true of DynamoDB, of course. But we are going to have a serverless version of Aurora database coming up soon as well. And then you've got storage services like S3 or Google Bigquery, which is a very good analytic platform where you don't pay for it when you're not using it, and you don't have to worry about scaling up to having thousands of nodes. So many people, including myself and Simon Wadley, who is a noted advocate for serverless paradigm, strongly believe that in the future, maybe in a few years' time, serverless will become the norm. It will become the de facto way that we build and deploy and run software. For many good reasons. Starters, chances are you're going to get a lot more scalability out of your serverless application compared to something that you host and run yourself. I know Amazon's got some scaling limits. Many of them are soft limits for your own benefits. And with Lambda, you can scale up to, I think, 500 new instances of a function every minute, which, even though it is a somewhat hard limit, but it's still a lot faster than most of us can manage with our own Kubernetes cluster, for example. Imagine how much capacity we have to have spare and just sitting around paying for them and not using, just so that we can spike into those capacity when we do need them. And with Lambda, Amazon is providing all those spare capacity sitting around. Amazon is paying for it, so their customers can can scale into when they need it. So it's much better for us when we don't have to pay for those additional capacity when we don't use them, and also it's good for the planet as well. And of course, the fact that you don't pay for something when you're not using them means chances are for a lot of your workload, you can have them a lot cheaper. Imagine you've got a server that all you're doing on that server is you run some cron job once every hour. So for the 59 minutes and 50 seconds of that server, you're not doing anything and you're still paying for it. But if you move that workload to Lambda, then all of a sudden you only pay for the 10 seconds when your cron job runs. And out of the box, you get multi-AZ and redundancy as well, which again, if you want to do something yourself, that is something you had to build into your architecture. With Lambda, you get multi-AZ out of the box, and with a little bit of work, you can also have your system being deployed to multi-region and using new features from API Gateway and DynamoDB to have a multi-region active setup for greater redundancy as well. We'll talk more about that later. But I think for me, the biggest reason to go serverless is that from having a great idea to having something actually running and being able to test the idea against the market, there are just so many things standing in my way, from choosing the right language and framework to learning the language and framework to figuring out how we're going to do continuous delivery, figuring out the pipeline, configuring the capacity we're going to need, configuring the ELB and so on. There's a lot of things in our way before we can actually have that idea running in production and start testing against the market. With Lambda or serverless in general, a lot of those things becomes trivial or they becomes irrelevant. Things like automated deployment becomes so simple with frameworks like serverless, or if you like SAM from Amazon, and with ELB and things like that, you don't need to worry about that anymore. A lot of that comes out of the box with services like API Gateway. So in return, you get far greater velocity to go from having that great idea to actually being able to test the idea against the market. And you do that by reducing what we call undifferentiated heavy lifting. So that's provisioning servers, managing servers, all the other things that you tend to do around the infrastructure, and let Amazon do a better job for you instead. At the same time, once your system is running, you reduce the amount of operational responsibility that your team have to carry. And it doesn't mean that you don't have to worry about ops anymore. Serverless is not a silver bullet. It doesn't necessarily remove all the operational responsibilities from you, but it does make them a lot easier. I did a previous talk, a different talk specifically on how you do ops in the serverless world in terms of monitoring, alerting, and logging, and so on and so forth. So feel free to check it out. And in one of my previous companies, I worked on a piece of a non-trivial serverless architecture where I moved the social network from running on monolithic Node.JS application to pretty much running entirely on serverless. And along the way, I learned quite a few things. And one of the key things I learned is that event-driven architectures has become commonplace with serverless. I think in part because technologies like Lambda and Kinesis has made them so easy to do. And events, they are a great way for you to build systems in a loosely coupled way where different subsystems are connected together only via events rather than being tightly coupled between them. And Lambda becomes a glue that connects the various parts of the system together. And over time, we see people compose Lambda with other services in a certain way, and a certain patterns start to emerge. So that's what we're going to talk about today, a number of high-level patterns as well as low-level implementation patterns. But before I start, I should give you some warning, as customary to, well, it should be customary to any talk that touches on design patterns, that you should know that design pattern is not a recipe for success. By definition, a pattern is just a repeated way that something is being done. There's no preconception on whether or not that way is the best or is even a good way. Maybe just the way that people tend to discover as they try to learn serverless. And following design pattern is no substitute for you to really understand the problems that you're dealing with and the constraints that you have to work within. And if you're not careful, as the context beneath those design patterns or those best practices start to shift around, what you consider as best practices today can easily become tomorrow's anti-patterns. I guess what I'm trying to say here is that I'm not here to show you some magical elixir, and there's no silver bullet. We should stop looking for them altogether anyway. Serverless is not a silver bullet. It's a great technology for great many use cases, but don't ever think about serverless as a silver bullet that's going to solve all of your problems. If anything, it solves many problems, but introduces other challenges that you now have to understand as you go into the world of serverless. So with that, let's look at some common patterns people do with serverless. And the first one is pretty good in that, as I talked about earlier, when you've got some cron job that's occupy an entire server, and you're paying for that server when you're not even running those cron jobs, and you can move those cron jobs into a Lambda function, and then you can have a CloudWatch event that triggers this function, say, once every 5 minutes, and in this case, in CloudWatch events pattern, you can schedule, you can say, when that happens, call a Lambda function. And equally, you can use that to automate a lot of your operational things that you do manually. For example, whenever from your Lambda function you write to standard out, that gets captured by the service itself and shipped to CloudWatch logs. And CloudWatch logs are really sucky for searching. You can't even search it, for across multiple functions. So instead, you have to go to individual functions, go to the log and search for that. So nobody really wants to do that. And what people tend to do is they will go to the console, they will say, for the log for that function, I'm going to stream it to another Lambda function, and from there, I'm going to ship my logs to something like an LStack. So it could be Elk, it could be Splunk, could be anything. It could be whatever log aggregation service you want to use, really. But what I want to talk about is that particular step where you have to go, someone have to go to the console and do a manual step to subscribe your logs to your log shipping function. So what you can do instead is enable CloudTrail on the account so that you can start to capture API calls that happen in the system that are done on your behalf. And then you can go back to CloudWatch events, create a pattern so that whenever this create log group API call is made by the Lambda service, whenever you create a new function, you can then invoke another Lambda function whose job is to go to the log group, subscribe it to this log shipping function you've got, so that whenever you create a new function and therefore create a new log group to go with that, you get the subscription automatically. So you don't ever have to think about yourself in terms of, oh, I created a new function, now I have to make sure that my logs get streamed to my log aggregation service. That all gets automated away using this simple pattern. And turns out this pattern is actually quite repeatable. And you can use that to do a lot of interesting things. For example, I've been writing about on the Medium recently how you can actually use it to automatically create dashboards and create alarms for your APIs. So whenever you say deploy API to API gateway, and you can have an event against that create deployment API call that API gateway makes for you, and then you can automatically inspect your API, find out all the endpoints you have in your REST resources, and then create corresponding alarms against, say, 400 errors, 500 errors, or latencies, or 95 or 99 percentile latency, so that you don't ever create a new API, deploy, and then you walk away and forgetting to create those alarms. And when things go wrong in production, you have no idea, because guess what? You don't have those alarms. And equally, you see people have the conventions around the team around what you should have in the dashboards. So if it's convention, then don't force people to have to remember to do it. Instead, automate it. And with CloudTrail, CloudWatch Event, and Lambda, you have all the tools you need to do that. Besides that, you can also automate other things around the security inspection. So with CloudTrail, you can also get events for whenever someone logs into the console. So if you're seeing attempts to log into the console at 2 a.m. or from a location where you have no staff, then maybe something fishy is going on. So when that happens, you should alert yourself right away. And another thing I learned from my friends at AWS is that, you know how you tend to, whenever someone accidentally posts their AWS credentials online, then minutes later, someone's going to be creating EC2 instances to do Bitcoin mining, and it turns out the hot sort of region for doing that for attackers is in Sao Paulo and then Tokyo. So when you see EC2 activities in regions where you don't have any infrastructure, then again you can use those automation tools, patterns to stop what's happening right away. And outside of the ops guys, you also have a lot of application developers building web APIs using Lambda. And imagine you've got some single page application in S3 that is exposed through CloudFront. And then on the back end, you have Route 53 talking to API gateway, which is backed by a Lambda function that's talking to a DynamoDB table. And if you want to do authentication, you can also use Cognito service as well, which out of the box implements most of the user flows you tend to have to do yourself in terms of registration, verification, sign in, sign out, change passwords, and so on and so forth. And out of the box, Cognito gives you a number of best practices, or rather good practices, such as making sure that the passwords are handled using the secure remote password protocol, which essentially means that the password itself is never exchanged anywhere. Only the hash of it is stored and also communicated over HTTPS. It also makes sure that all of your data is encrypted on the server side and supports capture, MFA, and so on and so forth. Another thing I see a lot of people do with Cognito is that you can have a third-party identity provider like Google or Facebook or Twitter, and then from the client application you can get your JWT token from those providers, and then using Cognito federated identities, which is another sub-service for Cognito, you can say, here's my token from Google, and then it will go and validate your token, and if it's a valid token, then it actually returns you a temporary credential for your client application, which can then be used to access any number of AWS services, including your own APIs. So if you're creating an API that you want to control access via IAM permission, then you can actually do that by issuing a set of IAM roles that has got access, that has got permission to talk to your API. Or if you've got services, for example, you want to talk to user IoT, that's something you have to do yourself. And if you find that you're building APIs that the only value that your code provides is authentication, then why do it at all? Just let the client talk to Kinesis or whatever directly if you want to do you want to track events from the client without having to go through an API yourself. And when you've got APIs, another thing you want to think about is how do you make sure that you have multi-region set up so that you have better response time for for your users, but also in terms of resilience as well. And nowadays, DynamoDB has got this thing called global tables, which allows you to create a table that is replicated to multiple regions in the world. And with API Gateway, they now support what is called region endpoint, which essentially allows you to create your own CloudFront distribution in front of it, which we just did today. And with a bit of work, you can actually set up a multi-region active setup with API Gateway and Lambda and Route 53 with not that much effort. And a friend of mine who's now working for AWS now, Alex Castaboni, did a really good webinar on how to do that yourself recently. And let's talk about how you're going to build a data lake or data processing pipeline. And in Amazon, S3 is your de facto choice for the data lake where you put all of your data into. And you can control access via IAM permissions, and you can make sure all of your data is encrypted using KMS. And nowadays, you can also use a service called Macy, which uses machine learning to scan the data that you store in S3 to look for secure sensitive data, and including personal identifiable information, PII, as well as API keys and tokens and passwords and so on, so that if you accidentally put those things in plain text in your S3 bucket, you can get alerted pretty quickly, especially with, now that GDPR is in full effect. That's going to become more and more important as well, that we don't accidentally put people's PII information into S3. And to get data into S3, you see many people use Kinesis, whereby your application would be streaming events into Kinesis, and then using Firehose, you can batch those up and then send them into S3, again, without having to write any lines of code. It's all just configuration to say the source Kinesis event, stream, and the destination bucket, without having just a simple configuration they can automate using CloudFormation. If you want to react to the events and do other things, you can have a Lambda function connect to the stream. And if you do some transformation before those events get put into S3, you can also hook up a Lambda function to Firehose. So this is where you can do some transformation in batch, so that before the file gets stored into S3, you do some transformation with a Lambda. And of course, once the file gets dropped into Lambda, into S3, you can then also trigger some other other processing with Lambda. For example, maybe you want to process all the events that you've aggregated through Kinesis and then batch update some index you have in the Elasticsearch or some table you have in DynamoDB. Again, you can do that pretty easily. And this is something that I've done for a very long time. I've used Google Bigquery since about 2010. It's great for doing big data, also BI workload. It's designed to work with exabyte-size data sets. And what we do is all of our applications, both the client and backend, will stream events of state changes in the system to Kinesis, and then by the time it's dropped into S3, trigger a Lambda function that will live stream all the events into Google BigQuery so that our BI guys can start to run ad hoc queries against those data. And I think last year or 2 years ago, Amazon announced a competitor for BigQuery called DAZN, which again allows you to run ad hoc queries against data you have in S3. And the result from those BI and those ad hoc queries can then be visualized using QuickSight as well. So you can actually have an entire data processing pipeline if you don't want to do any customization without having to write any code at all. So and all of the services can be arguably considered as a serverless technology because you don't worry about the server, there's no server for you to manage. How are we doing on time? 20 minutes? All right, so let's talk about some, implementation level patterns. The first one comes straight out of the SOA patterns book called the decouple invocations, which is a really good pattern when you want to deal with business logic that takes quite a long time to complete and you don't want the user to wait. And it's also quite important in the serverless as well because you have additional limitations to deal with. With API Gateway, for example, there's a hard limit on integration endpoints for 29 seconds. So your function can run for 5 minutes, but API Gateway is going to give up after 29 seconds. Which means if your endpoint have to do anything computationally expensive or just takes a long time to do, then 29 seconds, it's going to give up. You're going to have to respond to the caller before the 29 seconds. So what happens if you're dealing with downstream systems that are just not as scalable? I mean, in fact, at DAZN, we have to deal with so many third parties whose systems are, quite frankly, belongs to the last century. They're just not as scalable as what you would expect in these days and age. And if you hit your downstream systems, every time you get a spike in traffic yourself, you're going to project all of those spikes in traffic to your downstream, and you're going to go past the maximum throughput that your downstream system can handle. You're going to cause them to slow down, to start to timeout, to start to error, which if you're not handling those error cases yourself, then it's going to cause your own service to start to error and timeout as well, and you end up with a cascade failure throughout the whole system. And as the name of the pattern suggests, the decouple invocation decouples the reply from the initial request. So what will happen is, suppose someone makes a call to your post endpoint and say, hey API, go and do something. And you say, all right, sure. And in the background, in the meantime, you queue up some work for some background worker and you respond with a 202 and the location for where the result would be once it's ready. And on the client side, you would poll for the result every now and then, maybe every 10 seconds, and until the result is actually ready, you're going to keep responding with 202 with a location, and then when the work is finally being done by the background worker and informs the API, then the next time someone polls, you say, great, now finally it's all done, and here's a 200 with your response. What this pattern can also help you do is amortize spikes that you experience before you pass them on to your downstream directly. So if you cap your worker, if you're able to control the parallelism you have in the worker, that means any spike that you experience is not going to be projected onto the downstream, and instead your worker will process as much concurrency or parallelism as he can, but never ever going above what your downstream system can actually handle. So any spikes that you experience will just get amortized. They will just get processed a bit slower, but it takes a bit longer. And then the nice thing about this pattern is that even though if you're doing work that can take a long time, you can still reply to the caller earlier, so that or from the client's perspective, you can get a response back knowing that the work has been accepted, it's not finished yet. And you can do some clever tricks in the UI in terms of how you communicate those status changes in the same way that when you send a message to WhatsApp, that is a very classic asynchronous communication where you get one tick for when the message is in the the buffer on your phone, 2 when it gets sent to being received by the server, and then I think 1 blue tick for when someone actually received it on their phone, and then 2 blue tick for when they have actually opened it and read the message. So you can do very similar tricks in terms of on the UI side of things to improve how you communicate those different various stages to your user. And by removing this urgency to give the right answer right away, it means that you also give yourself more time and more flexibility in terms of how you deal with errors and how you retry those failed processing. So let's walk through one simple example. Someone makes a post request on API gateway that calls a Lambda function, which in this case is going to put some metadata into a DynamoDB table for the task they want to do when it was created, and the fact that there's no result just yet is null. And in the meantime, I'm going to queue up some tasks in SQS, and in the background, I've got a polling job that posts SQS every, 10 seconds, and it's going to try to process as much messages as I can. And then in the meantime, I'm going to respond with a 202. Oh yeah, remember that I've got a created add timestamp, that just so that we have a way to time out the user from polling forever. So the next time someone asks, is my result ready yet? And they check the database, nope, it's not ready yet, so I'm going to respond with a 202, and then eventually my background processing is going to be done, and it's going to update a DynamoDB table with the result. And the next time someone asks, is my result ready? You can say, yep, it is, and here's a 200 with your response, with the result of your task. Instead of SQS, which is not yet natively supported event source for Lambda, so that means you have to do some stuff yourself in terms of how you get Lambda, how you get those tasks from SQS into your Lambda function. Popular way to do it would be using a cron job, so that you trigger a Lambda function every, say, 10 seconds, and inside of that function you pull SQS. But Amazon announced at the AWS Summit in San Francisco I think a couple of weeks ago that it will become an officially supported event source for Lambda sometime this year, hopefully before reInvent. But besides SQS, you can also consider other event sources like Kinesis streams or DynamoDB streams. But if one of the purpose for you to do this pattern is a multi-spike in traffic, then it means SNS is a very poor choice. Because with SNS, I should probably mention as well, with Kinesis and DynamoDB streams, you can control the degree of parallelism with the number of shards. With DynamoDB streams, you can't really control the number of shards yourself, but it's kind of implicitly implied based on the traffic. But with Kinesis streams, you can say, this stream has got 5 shards, and therefore every shard has got its own Lambda function, and therefore you will have only a maximum degree of 5 parallelism because you've got 5 functions or processing events from Kinesis. But with SNS, every time you publish a message, it's going to kick off a new invocation, and therefore, again, you're back to having that 1-to-1 ratio of traffic that you experience to traffic that you expose and push down to your downstream. And then let's talk about a popular pattern that I guess most of you are familiar with, PubSub, whereby you have a broker between the producer of events and subscribers, and the same message gets routed to every subscriber. And this pattern is good when you want to decouple your data processing, and you can allow your subscriber to fail independently, so that if one of them fails, it doesn't take down the whole thing. And it means that partial failure is a bit easier to deal with as well. And again, you can configure, you can consider using SNS or Kinesis or something else as your broker. I think here SNS is kind of the de facto standard or de facto choice many people will go to. And with SNS, you get some nice qualities in terms of the number of retries. So when your function errors, for whatever reason, you get 2 retries out of the box, and you can also configure the function to have a dead letter queue, so that when the last retry attempt is made and it still fails, then that event gets sent to a dead letter queue that you can then go and fetch it yourself and maybe do some manual intervention. But as we talked about earlier, with SNS and Lambda, is 1 invocation per message, and therefore we need to worry about in terms of the amount of load that we put onto our downstream system, if that's a concern that we need to deal with. Another thing to keep in mind is that because every time you fire a message into SNS, it's going to trigger the Lambda function right away. So if there's some temporal issue, so something's happening right now, then you can be affected. So if imagine, again, talking about a downstream system that's got some maximum throughput that you can't exceed without getting into trouble, and you experience a spike. In this case, because you got retries, those retries will hopefully deal with those errors that you experienced during the spike. unless the spike itself is prolonged, so it goes on for a long time. So even the retry is going to fail because you're going to be so far over the maximum throughput. And also, if your downstream is having a really bad day, it was just down and just having some really bad outage, then any message that you try to process in that time is just going to fail. So with Kinesis and Lambda, you have a slightly different set of qualities that you can take advantage of. With Kinesis and Lambda, when your function fails, Kinesis is going to call your function again a few moments later with the same batch of records. And you keep doing this until either the data is no longer available or your function returns successfully. And with Kinesis, you can control the degree of parallelism that you have with the number of shards. So in terms of the temporal issues that we talked about earlier, well, for starters, you can amortize any spikes of traffic, as we talked about earlier, but because everything gets retried until success, it means that when your downstream is having an outage, even a prolonged outage, you will just keep on retrying anyway until eventually the downstream comes back online, and then you continue the process, and you're not going to overwhelm the downstream with more work than it's able to do because you can control the degree of parallelism. But what about DynamoDB streams? You can essentially achieve the same thing with DynamoDB streams as well. So a good question would be, well, should I use Kinesis or should I use DynamoDB streams? And I think to answer that, you have to go back to what is your source of truth. For most systems that we're building, the source of truth would be what's in the database. So something gets written to the database means that it's canon to the state of our system. As far as our system is concerned, it has happened. But what if you've got an event source system whereby instead of the database being the source of truth, is the event stream itself? So for systems like CQRS, for example, as soon as you write something to the stream, it's considered canon to the state of a system. And the fact that there are all these other background processes that need to happen, well, that's just that's just what it is. But as far as whether or not that is something that has happened in the system, as in terms of the source of truth, what's in the stream is the source of truth. And with DynamoDB streams, you also have a few things you need to consider as well. That firstly, you're limited to only the data that is stored in that particular table. Whereas with Kinesis streams, you can have a stream that represents various kind of things that happens around, say, the user, even if the data is stored in different tables. Another thing I find with DynamoDB streams is that the event describes what happens inside DynamoDB table. So a row being updated, a row being deleted, a row being inserted, and they don't really describe what happens in my system. What I care about are domain events like a user being registered, a user has created an account, they've updated a profile, and those are the events I want to deal with, not to have to mentally map row being added to a table into a user being created event. And interestingly, DynamoDB actually auto-scales the number of shards based on load. So if you've got a table with a lot of throughput, the number of shards is going to go up as well, which is a great thing. It means that, well, in some cases, because it means you don't have to build that yourself. In fact, personally, I have to build a system to auto-scale Kinesis streams several times at different companies. With DynamoDB streams, you don't have to worry about that. On the other hand, it also means now you have less control over the degree of parallelism. So if that is something that you need to worry about, then DynamoDB streams is going to give you less control in terms of what's the maximum parallelism you are going to experience. Another thing to keep in mind is that with Kinesis, you can extend the data retention to, I think, up to 7 days or 14 days. But with DynamoDB streams, you are limited to 24 hours. And interestingly, DynamoDB streams is charged based on the number of read requests you made. And even more interestingly, when you read them from Lambda, it's free. I don't know why they made this decision, but which means if you're processing events from DynamoDB streams with Lambda, you kind of get a stream for free. So let's look at how it's going to compare in terms of cost on very different options. DynamoDB streams, you still have to pay for the right throughput units, but it's relatively cheap by comparison. So if you're talking about 1 message per second for a whole month, that's how you're going to pay for each one of them. So on that basis, you may think, well, Kinesis is actually quite expensive by comparison, right? It's like order of magnitude higher than this guy. But what happens if you scale that to 1,000 messages a second for a whole month? Now the picture looks quite different. Kinesis all of a sudden looks very cheap now because, again, with Kinesis, even though there's a baseline cost in terms of you have to pay for at least one shard, but the cost based on per million requests is a lot lower compared to the other event sources, and therefore at scale it can work out to be a lot cheaper. Of course, don't take those projections as a face value. Your workload can be quite different. All of those price points, they are different based on the size of your payload as well. And you also don't have to stop at just using one pub/sub. You can have one pub/sub linked to another pub/sub. And you may want to do that if you want to have to publish to downstream systems that are not natively supported by SNS. But if you do this, you now have to take on responsibility in terms of handling retries and partial failures. So imagine your Lambda function is publishing events to a whole bunch of things. If one of these guys fails, what do? Do you retry everything? Do you then just keep retrying this guy? How do you, in terms of implementation side of things, how are you going to make sure that actually works? So the last pattern I want to talk about is a Saga pattern, which is a useful pattern for managing failures in the distributed transaction, which is something that we tend to do quite often when you come to the world of microservices. And there's a really good talk by Katie McCaffrey, who's an engineer at Twitter, on the Saga pattern itself. And in her example, in her talk, she talked about this example for travel booking system, whereby in one transaction, you're going to book the hotel, you're going to book the flight, and you're going to book your car rental. And if somewhere along this line, say you've done this too, and this guy fails, you need to roll back the entire transaction, including rolling back any state changes that's been made so far. And this system, you can model the action, so booking something, with as well as the rollback, as in terms of the canceling the booking for your flight, as a Lambda function. So I got my actions there, and I got my compensating or rollback actions there, all modeled as Lambda functions, and I can use a step function, state machine, to represent the entire workflow. So in this case, I have a simple workflow here that goes book a hotel, if you succeed, go to book for a flight, and then go to book a rental if everything's good, and otherwise I'll have to roll back and execute the cancel hotel action. So suppose I want to go from London to Dublin, I can execute that will be my happy path, and then if the hotel fails, then I have to roll back any changes I made at this point, and if the booking for the flight fails, then I have to cancel the flight and then cancel the hotel as well, and so on. And you can check out the code. It's all available on GitHub. Sorry, I'm over time, but you can find me in all of these places. I'm going to be talking about something a bit more advanced tomorrow in terms of how do you do chaos engineering with serverless at the AWS user group. And I also have got a course on Manning, so if you want to find out how to do ops with serverless, go check it out yourself, and you can get a 40% off with that code. So with that, thank you very much. I know I'm over time, so
if anyone has any questions, go through.
Okay, you got a question there from Joe?
If you're writing a web API,
yep.
What kind of things do you take into consideration when you're considering whether to use Lambda or not, or serverless?
So in terms of when you're building a web API, what sort of things you have to think about in terms of using Lambda or something else? The biggest one is cold start. With Lambda, you have so cold start is what happens when a new instance of your function is spawned in the first and runs for the first time. And when that happens, a bunch of other things need to happen in terms of imagine Amazon needs to spring a container and need to initialize the node runtime, you need to load your code, and so on and so forth. So typically you see maybe with Node about 500 milliseconds in terms of the latency for cold start. And that may not be acceptable for many people, and I know for sure that a lot of people are now looking at using Lambda for background processing, but not with APIs because of concerns around cold starts. What I would say is that you need to understand what is your requirement and also what is your traffic pattern. So even if you've got an API, you worry about a cold start, but if you've got pretty steady and predictable traffic, then you can do all kinds of things to make sure that, for example, you can pre-warm the functions by hitting hammering the endpoint before the real traffic comes, and then you create you spawn enough concurrent functions, and then by the time the traffic comes, then you have enough concurrent execution running without having to waiting for Lambda to create them. But of course, it doesn't mean that you now have to you now have to forgetting about scaling. You have to worry about scaling yourself, which kind of breaks the abstraction layer. But unfortunately, right now, that's what we have to do. With the Lambda team, though, they are doing all kind of things to improve code style in general. I was just talking to some of the guys. They are using Azure functions. By comparison, Lambda, in terms of the code, how it handles files, there's no unzipping. So with Lambda, they moved to SquashFS, which essentially basically allows you to mount the zip file you upload as a drive and just load your code right away without having to unzipping and all of that. So the effect of that means that you have a lot more predictable and also lower code start time by comparison. And you can also, if you use the languages like Python, Node.JS, and Go, you also tend to experience far lower code start time compared to other languages like Java or .NET. Another thing, there's also other things you can do in terms of making sure that every single endpoint is handled by only one function rather than one function for the entire API, and you do the routing yourself. It means that your individual functions is doing less and therefore has less dependency and therefore less time spent on initialization in your code. And yeah, so those are kind of things that you need to think about. There's also the 500 per minute scaling limit, and also API gateway. The default has with API gateway, the default is 10,000 concurrent requests per second, but again, that is a soft limit that you can get Amazon to raise. And even the 500 per minute scaling limit with Lambda, turns out that's something that you can negotiate as well if you have the right channel. So yeah, to answer your question?
Yeah.
Cool. Rob?
The other thing is that 24 hours is not a hard limit for the DynamoDB stream. You can get a bump up to 72.
Okay, you know.
Yeah.
What's the maximum now?
I think it's 72.
72. Okay, cool. Good to know. Anyone else? Okay, got a question there.
Ever use the maximum receive rate coming out of SNS?
The maximum receive rate out of SNS, no, I haven't.
We use it to control the thing you were talking about.
Okay.
With the load on downstream APIs, you can max out at 70 requests a second.
Okay.
And put the Lambda behind the API gateway and do it that way.
And you can configure that per topic or?
Yeah, you can do topic or subscription.
That's very good to know. Thank you. Anyone else got a question there?
So in your presentation, you showed like a lot of integrated systems with each
Yep.
other. But is it possible to use, well, let's say if I have on my own server a running UI, running server, and so basically I need to, as an example, just the Cognito, if I'm mistaken, for authentication. Can I use just that little bit without using the rest of infrastructure?
Yeah, so with Cognito, you can have a custom identity provider. So essentially, that's where you have your own identity provider.
So it's going to go from my UI to the Amazon and then back to my server, like, and that can be like. So
that's something that you could do. Let me go back to that slide. Show navigation. 1 second, I'll get there soon. You're talking about this bit, right?
Yeah.
So imagine if you got your own identity provider up here alongside all those guys. So your client application would get the JWT token from your own identity provider. You pass that to Cognito federated identities. That's going to validate against your own identity provider, and then that's going to then say that inside here you configure IAM profile for anyone who's got a valid token. So you can return them the IAM permission, IAM credentials to then access other resources in AWS.